before in Barcelona, then he moved to Mallorca, in the Institute of Complex Systems. Now he's currently at the Institute of Theoretical Physics in Madrid, working in a group of Alvaro Alhambra, and he's going to talk about open quantum systems and detailed balance.
Yes. Okay. Thanks a lot for the introduction. So, yeah, the topic of this talk is the one in the title, but maybe it is a bit technical for the people who are not in open system dynamics. So the important part is actually this thermalizing Lindblad equation, which means we aim at deriving from a underlying unitary dynamics of a system coupled to a bath, something that is an effective description of the dynamics on the system, and we hope to find something that is also Markovian. So the framework in which we are is something like this. You have the system on one side, then an interaction that scales with parameter alpha, and then on the other side you have the bath that you already assume in thermal equilibrium. And you have this kind of a splitting between the Hamiltonian in three parts, where the interaction part you can generically rewrite in terms of operators that act only on the system and operators that act only on the bath. So when alpha is small enough, you expect the dynamics to become Markovian, because basically any information that passes through the bath basically doesn't have the time to pass back, because the dynamics of the bath is so fast that any information just gets erased before it can have any backflow on the system. And moreover, from the zeroth law of thermodynamics, you expect that at infinity, something like this will bring everything to thermal equilibrium. So you expect that also your system Hamilton-like system state will be the Gibbs one. So what you usually do is look at the evolution of your reduced density matrix, and it has this bit of ugly form, in which basically you have a first term here that is a unitary rotation, but additionally to your system Hamiltonian, you have something else called the lamp shift term, which is just a correction that comes from having an interaction, a finite interaction with a system. Moreover, you also see all this part that is basically the most general form of a map that generates basically like the most general generator of a trace preserving map. And this part here is called the rate matrix. It basically encodes all the details of the interaction with your bath. And then if you see, we use something that is called the frequency representation for your, these are called jump operators, are the part of the interaction that that acts on your system. And basically what this frequency representation does is just you take the eigenvectors of your system Hamiltonian and you connect all the ones that have an energy difference equal to omega. This is completely general. You can do it anytime. So once you have this, unfortunately, in general, the evolution you get from here is not, it doesn't generate a completely positive map. So it's not physical. And for this reason, you need some kind of a further approximation to make basically all endeavor worthwhile. So yeah. Exactly. So the aim is to find a way, an approximation scheme, to make this thing a positive semi-definite in some sense. So actually, your idea is the right one, because the most common way is just to see what this rate matrix look like. And you have this part, which is a positive matrix. And then you have some kind of auxiliary term, this exponential in front. And OK, we are always working with alpha being extremely small. So you expect this thing to be extremely large. And then just applying the Riemann-Lebesgue lemma, you know that this whole thing will become a delta. And once you have a delta in omega tilde, well, basically you have a positive matrix that is this one. and then the same jump operator on the left and on the right, you have a CP map. This whole thing was basically explained by Davis already in the 70s. And it has the two nice features that on the one hand, you can prove it generates a completely positive map. And moreover, you also know that basically you can prove that if the bath is thermal, you're guaranteed to thermalize. You're guaranteed to reach thermal equilibrium. So it looks like we don't have anything to do. Everything was done in the 70s. But unfortunately, there are two drawbacks, and that's where we enter. Because if you look at the spectrum of many-body systems, well, basically this width of the energy, like the energy just scales with the number of components of your system, whereas the dimension of your Hilbert space will be exponential. So it also means that the spacing between any two, like generically, the spacing between any two energies will be also exponentially small. So what you have is that this approximation that you needed to apply the Davis scheme only holds for alpha being exponentially small in the system size, which is a severe restriction on the applicability of this kind of formulas. Moreover, if you see like how this frequency representation was given, basically you have these eigenvectors of a generic many-body Hamiltonian. These are extremely non-local objects. So it means that even if you started with an interaction that was localized somewhere, now you have jump operators that act over all the system at the same time. And this is something that you expect not to be physical as well. So you have these main problems that Davis scheme has, and actually when you try to simulate open system dynamics using this kind of approximation, well, it goes very bad. So now the question is, how do you do, how do you derive something that is not going through this kind of scheme? We will do it in 3 steps. First, I will tell you about the principle of detailed balance, which will be the main ingredient we will use to prove that you reach thermal equilibrium. Then I will give you the overall, the general picture of how you do microscopic derivation of open system dynamics in the context of many-body physics. So you don't want to assume anything about the spectrum, you do it in general. And finally, we put these two things together, and we show that actually you have something that is guaranteed to be CP and also guaranteed to go to thermal equilibrium. So let's start with the detailed balance first. And to get a bit of the feeling of what this tells you, let's look at 2 microstates of a Markov chain. And these are like the equilibrium distribution. And you know that basically a Markov chain has this Pij as the components of your stochastic matrix. And if you compare these 2 transitions, a Markov chain that satisfies detailed balance will be satisfying this equation. So basically, if your Markov chain satisfies this principle, you have something that tells you that the probability of seeing I and afterwards J is the same as the probability of seeing J and afterwards I. So detailed balance is a concept that kinds of encrypts the idea that the microscopic dynamics should be time symmetric into something that is actually dissipative. And in fact, the first time that something like this happened, was defined, was with Boltzmann when he was trying to prove the H theorem. And he said, okay, this needs to be true. It needs to be true because we know that classical mechanics is time reversal symmetric, and the same thing should happen also for the rates. So another important thing that, and the reason why we use this principle is that once you have this property of the transition matrix of your Markov chain, this directly implies that P it's an equilibrium distribution for the Markov chain. So it also means that basically once you check that this is the case, well, you know that the thermal state will be, or let's say P will be one of the equilibrium distribution. Moreover, when you rearrange the whole thing, it is also quite nice because it is connected to what is called the bias rule in probability. And basically, in some sense, this is also an interpretation you can give, saying, okay, you have your Markov chain, and then you do the reversal using bias theorem, and these two things are the same. So you don't have a reversal for dissipative dynamics, but if you say the reversal is given by the bias theorem, well, this is like the same as saying your condition, like your matrix satisfies detailed balance. So, okay, all of this is nice, but it's for classical system. What do we do for, yes? Yes. No, sorry. No. So you mean this thing? Yeah, it's an order thing. Yeah. Yeah. These are the probability of seeing I, like the macro state I. So P is a probability vector, and instead of writing it P subscript I, it's like P. Sorry. No. Like. No. This is a property of the rates, and the rates don't change in time, and the equilibrium, I mean, it's a bit confusing because you have the rates that have this property with respect to a probability distribution. So it's like when you, yeah, yeah, and then you can, and then what you can do is define a probability at equilibrium. So you already reached equilibrium, so you're already in P. And once you're there, the probability Pij, this one with the comma, it tells you like the probability of seeing I and then J, and the other way around. If your Markov chain is a detailed balance. Yeah. This is the definition of a detailed balance. Like you can have like an equilibrium state in which this thing doesn't happen. So, for example, if you have something like a Markov chain with cycles, you can have like a lot of thing like probability going out, and then it's not balanced. Like every transition is not balanced, but the overall thing will be balanced. So you have funny things happening. Yeah, no problem. So anyways, what do we do quantumly? Well, this is like the best we can do is always try to reproduce the classical things formally. So what you have here is like phi is now a map, and you define detailed balance now in this form, in which phi is connected to its adjoint map through this multiplication operator, which still we haven't specified, but we know what it will do on diagonal matrices. Because on diagonal matrices, you know that you want to regain what the classical probability was doing. So basically, this thing will be a multiplication operator by the state rho, and just by asking this general thing, I still haven't specified which is the super operator doing this thing. In general, just by asking this, you know that that rho now will be the equilibrium state of your dynamics, of your map phi. So what are some candidates for this map M? So the most common one is just the multiplication on the right. So you take a matrix X, and then M is just like multiplying it on the right by the state. And this is what is called the GNS detailed balance condition. And in general, it's the most common one you see in open system dynamics literature. If you open the most common book in the topic, that the Breuer-Petruccioni, you will find this one, even if they don't say this is the case. But anyways, like Alinsky, who introduced, or rather studied this property back in the 70s as well, actually was using this kind of condition and noticed that this makes the like your map self-adjoint with respect to the usual covariance, which is also something interesting because it tells you that when you have now A covariance with A and you evolve one of the two, the overall thing will be real. So you know that basically this is something you can measure in experiments. And finally, maybe the most interesting thing of this whole thing is that it has a microscopic derivation, which is the Davis construction. So basically, till last year, this was the only detailed balance condition that had associated to Lindbladian derivation that was from first principle, even if what we can show is that the Davis construction is basically the only one you can do. Because what you can prove is that if you have a map phi, and then you do your, like phi, it's CP, let's say, and then you expand it in, on a basis, and furthermore, you also expand it in the frequency representation, what happens is that GNS detailed balance is exactly equivalent to asking that all the components with different omegas will cancel out from your matrix. This is what is called the secular approximation. It was exactly the thing that Davis was using in order to prove his Lindbladian construction. And this, we already know that it won't work for many body systems. Yes? No. Yeah, like this one you can prove. Yeah, no, I mean, it is an interesting thing because it's like if you had another way which you could keep GNS but avoid the Davis construction, then why would you need another definition of detailed balance? But so it's fair to ask. And actually, yeah, we have proven that no, there is no way out. You need what is called the secular approximation. So let's go to the next best thing, which is what is called KMS detailed balance, which is rather simple modification of the one before. It is just like multiplying on the left and the right in a symmetric manner, but they stay row. And why do I say simple? Because it is quite puzzling that if you try to modify GNS detailed balance, basically most of the time you end up with a modification that is exactly equivalent to GNS. And this is like the simplest version that is not equivalent to GNS. It's strictly more general. And moreover, once you use this definition, what happens is on the right, what appears there is the pet map of your map phi, which is quite interesting because it's like, okay, there is a bit of debate on this, but it's one of the generalization of the quantum bias rule for quantum mechanics. And maybe the most interesting point for this discussion is that this kind of a detailed balance you can prove is it doesn't imply secular approximation, so it can have some relevance when you look at many body systems. So the question now is, can we find a microscopic derivation? So how do you do microscopic derivation? Well, in general, what you're looking at is the reduced density matrix of your system. which appears, well, it should be trace on the bath, not the old trace. And we have a number of assumptions we make. The first one is no initial correlation, which is, in some sense, a minimal and general requirement. Minimal because we want to find a Markovian derivation, and you know that if you start with something that is not in tensor product, you can have an evolution that becomes non-Markovian at a later time. And then general, because basically this thing, you can always assume that you go back in time sufficiently long such that the system will be uncorrelated with the bath. Because at some, like all the correlation have to be there because of some unitary dynamics at the end of the day. So you just go to minus infinity and the things will be decoupled from each other. Then, okay, let's remind you about the form of your of the interaction. The second thing we ask, and this is also general, even if it doesn't look so, that the interaction won't change the average energy of the bath. And this is the condition written here. So basically, it tells you that when you have like an interaction with the system, on average, the energy of the bath will stay the same. And if this is not the case, you just need a renormalization of the system Hamiltonian, but it's something like super standard, and basically you can always assume it. Now, this last thing I will ask, this is a bit more restrictive. We ask the bath to be Gaussian. What do we mean by this? Well, that all the correlation on n operators can be decomposed basically using weak theorems. So basically, you have the trace of x1 to xn, and basically you can isolate the x1 term and then sum over all the other ones, like just in couples. This is a funny rewritement. Yes. Any operator. Yeah. So this is kind of equivalent to asking that your bath is not critical or like quadratic. It's like it's a bit of a restriction. It's a more of a technical manner. Like, I mean, we need it for making all the proof better. Many people in the literature, they say that you can prove it even without assuming Gaussianity. I wouldn't put my hand on it, but at the same time, it doesn't look so fundamental that there should be a problem to generalize it even to things that are not Gaussian. So, yeah, exactly. No, it's not local. Yeah, it's like it's a n arbitrary operators on the Hilbert space of the bath, and yeah, you don't need any tensorization or anything. Yeah. So okay, yes. Yeah, we'll go into that. Yeah. No. This moment is just like there's no like you assume that the bath to be thermal at the beginning. Otherwise, you won't have thermality at the end. Yeah. Yeah. At time 0. Actually, this derivation, this part of the derivation doesn't assume even thermality. It's like it works in general. So, but yeah, like when you will want to prove thermalization, you will need to assume that at time 0 you have a thermal state. Okay. If you have like quadratic Hamiltonian, it will like on with the quadratic in the sense of defined in terms of creation and annihilation operators, which are quadratic, it will satisfy this thing. Yeah. Yeah. No, no, because this is weak theorems, so it's like it will decompose basically. Well, yeah. Um, so, okay, the nice thing is that assuming Gaussianity allows us to basically express the rest of the derivation just in terms of this quantity here, which is called the BAT correlation function. And basically, it encodes the response function of the BAT to basically interacting with the system. And okay, for example, what do I mean by it will encode? Well, there are 3 timescales that appear in our derivation, and they are all given in terms of this CKL. The first one is called gamma 0, is a rate, and is given by the integral of the absolute value of C. Then you have tau 0, which is, well, given by the integral of the absolute value of t for C. And then k0 is the same thing, but with t squared. And for this part of the talk, we don't even need k0 to actually be finite. It's like, could be diverging. But gamma 0 and tau 0 should be finite for the rest to make sense. Yes? Yes, yeah. Yeah, this is something you do, like, because actually tau 0 is defined as this thing divided by this integral. And you do it because of basically when you have it, yeah, it's like for having cutoff that work well, basically. Yeah, okay. This tau 0, an interpretation you can give is that, for example, say your BAT correlation function is exponential with a constant tau. Well, basically tau 0 will be exactly this star. And in general, you can always see that tau 0 is a time scale that measures the memory time in your bath. Like the time that it takes when you put a perturbation on your bath for this perturbation to be completely lost in time. Moreover, gamma 0 also has a nice interpretation. And it comes from this result, which is completely general, like just follows from these 3 things, no approximation whatsoever. And it tells you that the rate of change of your reduced density matrix in the interaction picture is actually upper bounded by this gamma 0. So gamma 0 sets like the fastest rate of change of your of the dynamics of the system as induced by the interaction with the bath. Okay, and the other thing that you can see from this equation is that this rate of change will scale with alpha being actually with alpha square, which is the constant of that, like the coupling constant with the system between the system and the bath. And this will mean that if you now plot a generic component of your density matrix in time, well, for different alpha, you will have basically that the evolutionary of your thing will be like slower and slower in time. For this reason, it's customary to actually define a rescale time in which basically you take t to be like you take your state to actually be defined with a time t over alpha square. And in this way, basically, what happens is that all these 3 curves will be the same independently of alpha, for alpha sufficiently small. The reason why we do this is because at a later time in the presentation, you will see some of the bounds to depend on this on time, and this time in this case won't depend on alpha at all. It's like it's this rescale time, so it will be the same. Like at a fixed time t, you will be at the same distance from the equilibrium state. So this is needed for the error bounds to actually make sense. sorry again. The thing when you rescale the this inequality, the alpha disappears. So you get you got gamma 0. So like the rate at that point doesn't depend on alpha at all. Okay. So just a bit of notation. I will denote with hat everything that in which I took out the initial point, but this is just not to clutter the slides too much. And okay, how do we do a microscopic derivation? Well, you start with your unitary dynamics, and then you take the trace against the like the reduced trace over the bath, and what appears is something like this, in which you have, well, it's a bit complicated, but the main thing is that you have this K, which is an integral kernel, which will depend on the system, will depend on the bath, and also will depend on the whole history of rho, basically from the beginning to the time at which you are evaluating it. And this is the most general kind of thing. It's exact. It's like it's the one you don't want to work with. So what you do is like it's introduce a number for approximation, one after the other, in order to simplify this kind of picture. So the first one is called the Born approximation. And basically what it does is that you pass from the integral kernel here, which depends on the bath as well, to this integral kernel here, in which the dependence on the bath only depends on this CKL, the spectral, the bath correlation function. And the reason why this step is justified is basically the following. So the bath is, has an internal dynamics which is extremely small compared to the thermalization dynamics of the bath. So basically, any time that the system gives some energy to the bath, this energy will be dissipated very fast. The bath goes back to thermal state. So to the eyes of the system, it will look like the bath is always thermal. So you can assume that the bath is in a fixed position, that is the thermal state. And this is what happens, like what justifies this kind of step. Using basically the same kind of reasoning, you also have what is called the Markov approximation, in which you pass from an integral kernel that depended on the whole history of your evolution to something that only depends on the instantaneous value of your system. And basically, this is the same kind of thing. Like the bath, since it goes always back to thermal state, cannot retain any information about the past of your evolution. And finally, we also have something that is a bit more difficult to grasp from an intuitive point of view, which is called the Redfield approximation, in which if you see what happens between here and here is that this integral that here was up until a finite point actually goes to infinity. And okay, this is a bit more difficult to justify, but basically what it does is telling you that at a later time, which is basically non-zero, the evolution of the bath is so fast that it is as if it was always happening. So it forgets about the fact that there is a starting point of your interaction. And this is exactly what happens when you bring this integral from a finite value to infinity. So, okay, this is all standard, but the nice thing is that we can present error norms, error bounds for all these steps in one norm. So we know that basically the state, the exact state will be close to the Redfield state, basically at all time. But the thing is, also one thing is that this Redfield state actually admits something of a differential form. But if you see that there's a bit of a problem, because here on the left-hand side you have the Redfield state, and then you have the generator of your evolution, but then it is not applied to the Redfield state itself, but rather to the exact dynamics. So from a point of view of simulation, or of making this problem simpler, this is just as bad as starting with the exact dynamics from the beginning, because you have to know the exact dynamics at all time to actually construct this Redfield state. So something you can say is, okay, I just define another state, which is the solution of this differential equation. And if you see, like, the only change here from the equation upstairs to downstairs is that this is a real differential equation. Well, unfortunately, this is impossible, because in doing this step, you incur in an exponential error. And basically, so far, yes, in time. Yeah, all this error, if you define it like this, are basically constant in time. And then, like, also the errors between the difference between the derivative of one and the other are also constant in time. But then eventually what you'll see is something that scales linearly in time, and there's a reason for it. And now I'll tell you also why you get an exponential error. And actually, this is something that so far it was done in the literature all the time. Like if you look like at any error bound in the literature about the precision of your approximation scheme, they are all with a exponential dependence in time. And the idea behind the proof of this thing is quite simple, actually, which is we want to bound this thing, like the one norm between your solution of the differential equation and the exact dynamics. You do a triangle inequality in which this first thing, this first part, you know how to control. This is what I was saying. Everything in that part is completely controlled. But then now you have to understand how this other part actually scales in time. And the way in which you do it is basically taking a derivative and then integrating again. You bring the norm inside. And you have this kind of recursive relation, which you have like the same difference on the left-hand side and on the right-hand side. But on the right-hand side, you are applying this additional map L to them. And the problem is that at this point, this map L is not CP. So it is actually a characterization of not being CP, the fact that it will expand the norm at least on some vectors. So basically, since you have this kind of relation, now you can apply it again and again, and you get a recursive equation that basically will blow up exponentially fast. So in order to solve this problem, we need to do a step backwards and look again at like basically a diversion with no approximation. And as I was saying at the beginning, this kind of rate matrix, it appears with like a rotatory term. It will not be very fast in general, but it's there. And in this derivation, we didn't use this thing at all at any step. So something that we notice is that there's in the mathematical literature about differential equations, something called methods of averaging, which actually treats this kind of a differential equation. And it tells you that if you look at the differential equation, for example, this blue line, well, you can't see blue, well, the wiggly line here, that is the differential, like it's the solution of a of an oscillatory differential equation. It will always be close to something that is defined by taking the average over a period that basically scales as the inverse of your oscillation time. And basically, this is what we did. We introduced a new state that is given by taking the Gaussian average of the exact dynamics over basically some period t called the observation time, and then you just average its value over basically this Gaussian window. And once you do this, an interesting thing happens. That basically you can do the same kind of step you had before. So you have Born, you have Markov, you have Redfield, and the same kind of error estimates you had before are still there again. But now you have the space to give an extra step in which basically you find this row coarse grain, which can be expressed in terms of a differential equation. Well, here it's already like the differential equation. Well, in terms of a differential generator, which is CP. So at the moment of defining this differential equation with the rho G, what happens is you can do the same steps as before, but now, when you're estimating this difference, you have the fact that this L is CP, so the norm will be contractive. So basically, just by allowing like the change of your initial state, what you have is that the error between this smoothed state and the coarse grain version will scale at most linearly in time. So in particular, now what you have with respect to the exact state is that, okay, the second part is the one we saw here with this scaling in time. And now I put back all the constants. So you see that, for example, the time should be small compared to gamma 0. So if you have gamma 0 being extremely small, this will be a good approximation of basically at all times. Then tau 0 also appear there. And the other thing is that you see that there's an additional term which does not depend on time. And this term is actually arising because of this first norm. And the funny thing is that maybe this was the missing ingredient for previous derivation, because all the previous derivation were looking for basically finding an approximation scheme in which you have the same initial conditions and then a differential equation that was CP, and then proving that these two things were close together. Instead, what we do is saying, okay, at the initial time, you already have a small error, small in alpha. And this small error comes from the fact that at time 0, this is not the initial state. Something like it's an average over some time, but it's not the initial state itself. And but the nice thing is this initial error won't basically propagate in time. And moreover, it allows you for this extra approximation scheme that allows you to get a much better result. And something maybe that I should mention is that in order to get this kind of time scaling, you have to choose this time window to scale as 1 over alpha. You can choose different things, but we have proven that this is the optimal choice. So what does this Lindbladian look like? So it has this form in which you have now, again, some kind of a lamp shift Hamiltonian. And moreover, here you have that bat spectral density, the same kind of matrix that was appearing at the very beginning of the talk. And this is known to be a positive matrix at fixed omega. But now the jump operators are slightly different. They're not anymore the jump operator we had before, which were only this AK omega part, but rather they're basically given by a Gaussian average over many different frequencies. And this has some nice consequences. First of all, as t goes to infinity, this thing in front will become basically a delta function. So you go back to Davis approximation scheme. So we have an approximation scheme that is strictly more general and that reduces to the Davis one in the limit. And the second thing that is also quite interesting, T alpha is basically, so you see here I already put omega alpha to the power minus 1. It's actually omega of T alpha is the window over which you're averaging your trajectory. Yeah. Davis. Yeah. Yeah. So basically, um, actually, this is not even needed to go to strictly infinity. You need t to be bigger than the inverse of the smallest frequency differences. Yeah. Yeah. But once you have that, you exponentially fast go to Davis kind of maps. And it's quite interesting because he was doing all these bounds in infinity norms, which are not contractive over time. Instead, one norms are. So, like, well, anyways. Second thing, this definition of jump operators makes them quasi-local in time, even if it is not completely apparent from how they are given, because as I told you, these are non-local operators. The fact of having a Gaussian smoothing in front makes the whole thing quasi-local. And this is basically appears from the fact that you can do some Lieb-Robinson tricks, everything localized. Actually, you can cut the Lindbladian above to something that is strictly local. And basically the approximation error scales exponentially fast in the how local you want your jump operator to be. And yeah, also this thing is somehow related to energy time uncertainty relations, because basically in some sense it's telling you that your jump operators are not anymore doing the jump on a fixed energy omega, like a fixed frequency omega, but rather on a smooth envelope around your energy omega. And only if you allow the bath to have infinite time, so you can probe which is the frequency you want to jump, then you go back to basically having the Davis construction from before. So one last thing, maybe the reason why many people are interested in this thing lately is that this kind of Lindbladians are efficiently implementable on quantum computer. Because on a quantum computer, as soon as you have a Lindblad form with quasi-local jump operators, you can put everything in there. So in particular, there have been some proposal for detailed balance dynamics, Lindbladian dynamics, that were efficiently implementable on a quantum computer. And basically, they were invented by a couple of guys in Berkeley. And they were just like saying, OK, we want to prepare a Gibbs state on a quantum computer. So we present something that is completely artificial. And that's our motivation. And as I'll show you in the next section, basically, what they were doing is not just preparing the quantum state, but basically, in some sense, they were also, like when you do that algorithm on a quantum computer, you also simulate the open system dynamics of the corresponding state. So, OK, let's wrap everything up. So, as I was saying, this C is a positive matrix. So you can define something that's a matrix G, which is the square root of C, like the matrix square root. We also assume it to be the positive square root. And what we can prove is that with a small error, you can pass from this expression above to another one, which we changed the jump operator. If you see, like the tilde became a hat. And now the definition of the new jump operators is a bit ugly, but OK, basically the same. It's like you have a Gaussian envelope, and then this G function that already enter the jump operator definition, and then the usual jump operator in the frequency representation. So why do we do this? Well, with these jump operators, we can prove that this part of the Lindbladian becomes exactly detailed balance. So we don't have still a whole Lindbladian dynamics that is exactly detail balance, but at least this part, which encodes basically the distributive part, it is. KMS detail balance, sorry. Otherwise, it would be the Davis one. And the interesting thing is that there's a theorem that tells you that as soon as you have this part being exactly detail balance, then you can find a Hamiltonian term that when you add it to your Lindbladian, everything becomes an exactly detail balance evolution. So then there are only two steps left to prove. And we have shown that this correction, like this Hamiltonian correction you need to do, is actually small in alpha. And for the first time, beta appears there. It's like you have this exponential dependence on beta. And another thing is like, this is also the first time you have to assume that K0, that extra constant, was finite. So far, everything I said is general. But here, kappa 0 actually plays a role. If it's finite, and then everything works. Otherwise, well, you don't have a justification for this bound. Finally, we also prove that by changing the system Hamiltonian, and we normalize it with basically this coarse-grained lamp shift P's, you can get rid also of the extra term, the one here. So finally, putting all these steps together, we say, like we find that with an additional small error, you find this Lindbladian dynamics in which now these jump operators are defined with respect to the renormalized Hamiltonian term. Then this term disappears and is actually changed by this additional lamp shift Hamiltonian. And we have now basically proven that this thing not only will be close in time, like close to the exact dynamics with the same scaling as before, but also that you will reach the thermal state of this renormalized Hamiltonian. So basically, wrapping everything up, we started with an exact microscopic dynamics of a system coupled with a bath, and basically assuming only that the bath is thermal, that 3 timescales of the bath were finite, and yeah, basically that's it. You get that you have a KMS detail balance Lindbladian that represents accurately your evolution, and then eventually will bring you to something that looks like the thermal state you were looking for. And okay, this is not exactly the one you were looking for. It's with alpha square error, let's say. And there are two kind of approaches to this thing. It is a problem that was known in the literature. The first one is saying, okay, you're coupling your system to something else. The interaction will play a role. So you will have correction to your final state. And this kind of renormalization you need to expect. But there's also another approach that is the one we take in our paper that say, okay, if you see all the approximation we did were at order alpha. And now we arrive to a system state which is alpha squared close to the real thing. So actually, basically to what it matters for our approximation scheme, this is exactly the system state you were looking for. So yes, this is everything I wanted to tell you, and thank you for your attention. And yeah, any question you have, are welcome.
Okay, so question.
Yeah, thanks for this very nice talk. So regarding the point at the end, so ordinarily the lamp shift provably commutes with the system Hamiltonian. So
can you speak a bit louder?
So in the ordinary case, the non-many body master equations case, or GKLS equation, the Lamb shift term necessarily commutes with the Hamiltonian. Is it the same also for this? So now it can actually change the eigenbasis.
Yeah.
Rather than just shifting the
Yeah.
values.
No, I mean, it's a crazy thing. Because basically, this additional term, well, first, this additional term does not commute with the Hamiltonian. Also, this thing does not commute with the Hamiltonian.
Okay.
But the funny thing is, like, at equilibrium, there's a kind of a balance between this like unitary rotation and this part, so that basically everything balanced, even if this thing doesn't commute with this thing. So you have a unitary rotation that doesn't commute with your fixed point, but basically everything balanced out in such a way that magic works, and this is actually, like, even if you have a unitary rotation that should create coherences, it creates coherences at the same rate in which the dissipative part actually kills the coherences. So there's this funny thing. But also there's another thing that is a bit weird, which is, okay, this is at order alpha square. So there's something called the mean field state, or mean field Hamiltonian, that is basically saying, okay, we assume that eventually you reach the Gibbs state of the whole thing, not just of the system. So the Gibbs state of the whole thing, when you take the when you reduce it on the system, it won't look like this, but rather it will have some effective terms that comes from the interaction with the bath.
Okay, so
and this is not the same Hamiltonian. It's a different one.
that was going to be my next comment.
Yeah.
Okay.
No, it's a crazy thing. This is the problem they have in the literature, that the renormalization that comes from the dynamics is not the same renormalization you would expect from thermodynamics. So you have a static renormalization, like this dynamics renormalization, they don't coincide. They coincide within the order at which all these approximations hold, but they are not the same thing. They are all both alpha square.
Thanks.
Yeah.
I would have another question, but maybe I'll some space to somebody else. Well then, if I may, yes. I've forgotten it now. I'm sure I'll remember it as soon as I walk out the door. But if I do,
Okay, very good. Thank you, anyways.
I also have a question. I didn't understand exactly this trick when you try to substitute in the red field, essentially the approximation that doesn't work, this norm that you try to bound, this one norm that you say goes exponential because the Lindbladian is positive at some point.
Yeah. This thing.
Yes, this one that doesn't work for the red field, right?
Yeah.
So it could be also that, it's a bound. It could be that the inequality is not very tight.
Yeah.
And actually you get this bound that explodes, but actually in reality, so do you have also like an example in which really you can see that this error is bad?
Okay, I'll tell you even before that, like not even this inequality is bad. This inequality is bad. Because if you see, it's like this is a state, this is a state, like an exact state, upper bounded by by 2. And then the problem is, like, you introduce here something that is not a state, and this is not a state. So at this point, this trace norm can be anything. So basically, any time that the red field equation will develop some kind of negativity, you know that this thing becomes like already a step you shouldn't do.
Yes, but so it could still mean that you take the red field approximation and it is a good approximation.
Yeah, this is something that effectively is done many times. And maybe one of the way in which you can interpret this is that we didn't do anything magical. It's like all of these things are close to each other. The only extra thing we did is, like, now we have a way of saying that they are actually close to the, yeah. But the things are close to each other.
So regarding the non-locality of the jump operators,
Yep.
Why is that so much a problem? I mean, I would expect, given that the whole game of master equations on some level is about blurring out a certain timescale, one would assume that they should become non-local and actually quite non-local, I guess, in general, if you average over a certain timescale, right?
Yeah.
So
Like, I mean, in fact, if you send t to infinity, you go back to your Davis kind of scheme, and your jump operators become
Just
actually non-local.
But is there a problem beyond just that we're more comfortable with dealing with local stuff? Is that
I mean, let's say, like, it would be quite surprising that in general nature would need to act on the old system at all time instantaneously.
right?
Like, I mean, there are Lib Robinson in nature.
I guess the way what I'm thinking is there anything wrong with the perspective that that's just the cost of having a master equation from any body system, in a sense that if you're gonna blur out some timescale, you'll just get non-locality. That's if I
Yeah, no, okay, no, maybe this is something else. It's not about non-locality. It's like the secular approximation is like, it's very bad for, like, it doesn't, when you try to simulate like the
I mean, this aspect of it makes sense. Yeah, of course.
Yeah.
If you have exponential errors with time, then you're already screwed.
No, but this is not even about the approximation scheme I was saying. It's just like, in general, you check it, like you have the exact dynamics you can simulate.
You mean also for a single body open system now? Or
No. From anybody, you can see that the two things like diverge, like they're not representing the same thing. And basically, this happens because the thing that was behind the secular approximation, that basically was that this exponent was very big, it's not justified anymore.
So it's the non-locality that's causing the secular approximation to fail. That's what you're saying.
Yeah.
Okay, I see. There we go. Okay, yeah, cool.
Yeah. So it's like, I mean, non-locality is bad, but more from a moral point of view. It's like I would feel very offended by the nature if it was like, in order to thermalize something, you had to act at the same time over all the system. But from like strictly speaking, could be true. But the thing is, like, the approximation schemes breaks down. So it's like, even if this kind of a very exotic behavior were true, well, they're not justified. Like, and in fact, you can show by exact simulation that this is just not the case. It's like, unless you have very exponentially small coupling, then it goes back to be the correct way.
Okay, I see. Thanks.
Yeah, thank you.
So if there are more questions, let's thank the speaker again.